This is part one of Main Asteroid Belt. We start with the key question. Main Asteroid Belt, overview. Between Mars and Jupiter sits a region that most people picture as a dense, chaotic obstacle course. It isn't. And understanding what it actually is tells us something fundamental about how our solar system came to be. This is Orbital Dispatch, and this is the Main Asteroid Belt. Episode 1, Overview. The core question is straightforward. What exactly is the Main Asteroid Belt, and why does it look the way it does? It matters because this region isn't just a pile of leftover rubble. It's a preserved record, imperfect, yes, but readable, of the conditions that shaped the inner solar system roughly 4.5 billion years ago. Getting the overview right sets up every other question we can ask about this place. So let's start with where it is and what it contains. Then we'll look at how it's structured. And then we'll get into what that structure actually means. The Main Asteroid Belt occupies the region between roughly 2.2 and 3.2 astronomical units from the Sun. 1 astronomical unit is the average Earth-Sun distance, about 150 million kilometers. So the belt's inner edge sits at around 330 million kilometers from the Sun, and the outer edge at roughly 480 million kilometers. That's a broad band of space, and it's largely empty. That last point is worth sitting with. The belt sounds crowded. It isn't. If you took every object in the main belt and combined them, the total mass would come to somewhere around 4% of the Moon's mass. Every rock, every minor planet, every chunk of metal and ice, the whole lot weighs less than 1/20th of the Moon. Spread that across hundreds of millions of kilometers of space, and you're looking at an extraordinarily sparse environment. The belt contains roughly 1 million objects larger than 1 kilometer across, and many millions more smaller than that. But the distances between them are vast. When spacecraft first passed through, Pioneer 10 back in 1972 was the first, mission controllers weren't entirely sure what they'd encounter. As it turned out, the craft passed through without incident. The odds of hitting anything significant are very low. Now, here's a question worth holding on to. If the belt is so sparse and low in mass, why do we call it a belt at all? What shaped it into this structure in the first place? We'll come back to that. The objects within the belt aren't randomly scattered. They're sorted. And that sorting tells a story. The belt is divided informally into inner, middle, and outer regions. These correspond to different populations of asteroids, with different compositions, separated by gaps caused by a phenomenon called orbital resonance with Jupiter. Orbital resonance is worth a brief explanation. If an asteroid's orbital period around the Sun is a simple fraction of Jupiter's orbital period, say 1/2 or 1/3, then Jupiter's gravity tugs on that asteroid at the same point in its orbit, repeatedly. Those tugs build up over time. Eventually, they destabilize the orbit and push the asteroid out of that region entirely. The cleared zones that result are called Kirkwood gaps, named after the American mathematician Daniel Kirkwood, who identified them in 1867. The most prominent gaps sit at resonances of 3:1, 5:2, 7:3, and 2:1 with Jupiter. They're real gaps in the distribution of asteroid orbits, not empty space you'd notice flying through, but clear signatures when you plot the orbital data. The inner belt, inside roughly 2.5 astronomical units, tends to be dominated by silicate-rich asteroids, classified as S-types, rocky, relatively bright, and compositionally similar to some meteorites we find on Earth. The outer belt, beyond roughly 2.8 astronomical units, is dominated by C-types, dark, carbon-rich objects that have changed relatively little since the solar system formed. Between them, the M-types, metallic asteroids, add another layer of complexity. This compositional gradient, running from rocky inner populations to carbon-rich outer ones, isn't a coincidence. It reflects the temperature gradient of the early solar system. Closer to the sun, temperatures were higher, and volatile materials burned off or never condensed. Further out, more complex carbon compounds and ices survived. The belt preserved that pattern. Size matters here, and a few objects dominate the belt substantially. Ceres is the largest body in the main belt by a considerable margin, classified as a dwarf planet, the only one in the inner solar system, with a mean diameter of about 945 kilometers. Ceres alone accounts for roughly a third of the entire belt's total mass. It's large enough that its own gravity has pulled it into a roughly spherical shape. After Ceres, the next largest objects are Vesta, Pallas, and Hygeia. Vesta has a mean diameter of around 525 kilometers. Pallas and Hygeia are broadly similar. Below that, objects drop off rapidly in size. The vast majority of belt objects are small, irregular chunks, not the smooth, round bodies we might imagine. Temperatures across the belt vary with distance from the sun and the surface properties of each object. In the inner belt, surface temperatures might average around minus 70 degrees Celsius. Further out, it's colder, around minus 100 degrees Celsius or below. These are rough averages. The actual figures fluctuate with rotation and orbital position. Here's the detail that often surprises people. Ceres has a thin, transient exosphere, a very tenuous envelope of water vapor that's been detected around it. It's not an atmosphere in any functional sense, but it is real, and it points to water ice beneath the surface. The Dawn spacecraft, which orbited Ceres from 2015 to 2018, confirmed ice deposits and a surprisingly complex interior. Ceres is far more geologically interesting than it looks at a glance, which brings us back to the question I left open. Why is the belt shaped the way it is? Why so sparse? Why a belt at all rather than a planet? The short answer is Jupiter. The longer answer involves accretion, the process by which dust grains in the early solar system clump together under gravity to eventually form planets. In most parts of the solar system, this ran to completion over tens of millions of years. In the region we now call the main belt, it didn't. Jupiter's gravity kept stirring things up, increasing the relative velocities of objects there. Rather than gently colliding and sticking, protoplanetary bodies were hitting each other at speeds high enough to fragment rather than accumulate. A planet never finished forming. Over time, through Jupiter's resonances, repeated collisions, and a process called the Yarkovsky effect, where sunlight absorbed and re-radiated by a rotating asteroid exerts a tiny but cumulative force on its orbit, material was gradually cleared from the region. What remains today is a fraction of the original mass. There are open questions here too. Exactly how much mass was originally in this region, and when was most of it removed? How did the large-scale migrations of Jupiter and Saturn, early in the solar system's history, reshape what we now see? These are active areas of research, and they connect to models like the Grand-Tack hypothesis and the NICE model, which we'll get into as this series develops. What we have in the main asteroid belt, then, isn't quite a failed planet, and it isn't random debris either. It's a disrupted, sorted, partially preserved sample of early solar system material, one that we can study remotely with telescopes, directly with spacecraft, and occasionally handle when fragments arrive on Earth as meteorites. We have sent missions here. Dawn visited both Vesta and Ceres. Near Shoemaker visited Eros. Hayabusa and Hayabusa 2 returned samples from near-Earth asteroids with main belt origins. Our understanding has grown considerably with each mission. Next time, we look at formation history, how the belt came to exist, what it contained in the early solar system, and what displaced the mass we no longer see there. The full playlist is linked in the description if you want to follow this series from the start. And if this kind of careful, grounded look at the solar system is what you're here for, Subscribing is the simplest way to make sure you don't miss the next one. That is part 1 of Main Asteroid Belt. In part 2, we explore the next key question. Subscribe so you do not miss it.